now. All right, and with that, I give Ralph the control, and he will introduce to you the basic concept of machine learning and more about use cases and how to approach the machine learning problems. So I think, Ralph, we can start now. We have 14 participants today, and more may join as we go. So let's begin.
Thanks. Can you see my screen?
Yes, I can see your screen.
Okay, great. Yeah. Thanks to everyone for making it possible to join. We would like to introduce to you the basic concepts of machine learning and some terminology so that we have a better basis for the communication about the use cases and what we need for specification of the use cases from a machine learning point of view. Some of you are typing or doing other things in the background. I would appreciate if you can mute yourselves unless you want to ask questions. Of course, you can ask questions anytime you like. Just jump in and let us know if there's something that is not clear enough or if there's other questions. Okay, so what is the objectives of the webinar? The first idea is to understand the basic concepts of machine learning and data science. Also, we would like to introduce the most widely used standard for performing data science projects called CRISP-DM, for Cross-Industry Process for Data Mining. This is a methodology that guides you through a number of steps to have a structured and goal-oriented way of performing successful data mining projects. And we would like to introduce that because the first two phases of that process, called business understanding and data understanding, are quite important to address well for a successful completion of a machine learning task. And so it helps to understand the typically asked questions in those phases. Also, when we define the use cases, because in the ideal case, we answer these questions in the definition of the use cases. Then you would also like to identify some example business use cases and how they relate to machine learning tasks, and give an overview of some machine learning applications in the industry, just to give you some ideas. And then, of course, there's room for questions either between the topics I discuss or at the end. And also we can discuss ideas around use cases you already have in mind. So let's start with a question. Can you predict the future? Well, nobody dares to answer that. At least I don't hear an answer. Let's assume we are at a reception. Everyone is standing at a table. Everyone has a glass in their hand. Maybe it's a glass of champagne. Maybe it's a glass of water. And then you see that from one of your neighbor's hand, a glass is sliding. And the interesting thing is, if you now look around and the people that see that glass falling, you will see most of them will look shocked. The question is why? Well, they anticipate that the glass is going to break when it hits the ground. So that means they can predict that the glass is probably breaking before it even hits the ground. Typically, if you're standing and you hold a glass in your hand, that's a bit more than a meter, maybe 1.20 meters, depending how tall you are. And for that height, the fall takes about 473 milliseconds. That means a human can make a prediction in a fraction of a second. And the question is, how can humans actually do that? Well, the thing is, we have observed a lot of glasses fall when we grew up as kids and also as adults. And sometimes the glasses would break and sometimes they would not break. And from that, we have gained experience. We have created, unconsciously probably, a model in our head where we can predict how likely it is that a glass is going to break when it falls. It depends what is the height from which the glass is falling. If it's a low height, then it's less likely to break. If it's from a higher altitude, it's more likely to break. It depends also on the hardness of the floor. If it's a soft carpet, it's less likely to break. If it's a hard stone floor, it's more likely to break. Also, it depends on the glass itself. It's a very thick glass, like the water glass on that picture, then it's less likely to break. If it's a thin champagne glass, it's more likely to break. So obviously, we have not only learned to predict whether a glass is likely to break or not when it falls, we also identified certain properties to look for, like what's the height of the fall, what's the thickness of the glass, what's the hardness of the floor. And from the observations of the past, we have learned a model to basically predict whether or not a glass is going to break. So when I asked the question, can you predict the future? Obviously, you cannot predict the lottery numbers or other random things, but there are things in nature or in industry processes or in the telecom industry that follow certain physical and mathematical laws. And obviously, if there are such laws, then there is a chance that machine learning can help to find the underlying patterns, to find the underlying relations, and help to predict things. Not for every individual glass perfectly, but with a certain probability and with a certain accuracy. So in that sense, here we talk about predictive analytics. We analyze data from the past, observation from the past, to learn a model that helps to find hidden patterns in big data sets. And then with these patterns, we try to predict something, the future outcome of certain events. For example, what happens when the glass falls? Will it break or not? Obviously, we're not talking about glasses here in the telecom industry, but about other things. But I like this example because it illustrates a few things. First of all, we have data from the past, the observations, seeing glasses fall in the past. Then we have the process of finding patterns in this observation, in this data, to come up with a model that allows to explain and predict whether something is going to break and maybe give an explanation why it's going to break. For example, because it's a thin glass, it's a hard floor, and it's a very high altitude from which the glass is falling. So this is like a little example that already shows a lot of the things we talk about. We talk about patterns, identifying patterns in data sets, finding trends, finding correlations, or even better causal relations. That is, from data, we want to create models that enable the automated classification or prediction of new situations or cases, that allow forecasting of events or values, or prediction of risks and opportunities. When people talk about analytics, they often refer to different things. Some people, for example, especially in the business intelligence world, they use descriptive analytics to describe what has happened in the past. For example, you have different products that you sell in different stores, and you observe in some branches of your company, you sell certain products more often than in other branches. So the observation would just be, for example, observing which product was sold in which branch, how often. It's looking at the past, looking at some aggregated data. But it doesn't give you any clue why that has happened. It's just an observation. That's what's called descriptive analytics. The next step is trying to understand why it has happened. Why am I selling one product better in a certain area than in another area? That's also called diagnostic analytics. It's trying to find explanations with data mining, trying to find the reasons, the patterns, why something happened. But still, I'm just looking at the past. Now, the next step is to use these patterns or models that I found to predict something, to anticipate what will happen so I can avoid risks, or that I can make use of chances, use opportunities. For example, if I see that something might break with a high probability, maybe there's something I can do to prevent it. For example, if I can predict a machine failure before it happens, maybe I can introduce a certain maintenance procedure to prevent the machine from breaking. That's also called predictive maintenance. And that actually brings us to the next level. So far you have gained insight, but you haven't performed any action yet. The next step is actually the analytics recommending certain actions to optimize the outcome in your interest. For example, to maximize opportunity, to minimize risk, to reduce costs, to maximize profit, whatever the goal is. And that is called prescriptive analytics. So the analytics tries to give you recommendations what to do next, what to do best to get the best outcome for your target. So looking at machine learning and data science, how do these things relate? Machine learning is a field that deals with algorithms creating or generating models from data from the past. And these models can be used to explain things or to predict things. And in machine learning, there's a whole variety of techniques coming from mathematics, from statistics, from logic, from rule-based approaches. There's a lot of different approaches, but they all have the same goal: make things explainable, make things predictable. And then there's a certain subset of learning algorithms called neural networks, and a certain type of neural network approaches that is called deep learning. So basically, deep learning is a subfield or sub-area of machine learning. And machine learning, again, is a sub-area of artificial intelligence. Obviously, capability to learn and to adapt to changing environments is a very critical part of intelligence. But there's also other aspects of intelligence that are part of the field of artificial intelligence. For example, logical reasoning and deduction, or automated planning, or something like logic-based control, or knowledge representation, natural language processing and understanding. Sometimes you can use machine learning to support these other tasks or the other aspects of intelligence, but there's more than just the learning aspects. So when we're using the term artificial intelligence, basically refer to all kinds of methodologies and approaches to make systems more intelligent, not only machine learning. So what's data science? Now, data science uses machine learning and techniques like deep learning and sometimes also other artificial intelligence techniques to solve certain application problems. So you could say it's a science of research about algorithms and their practical applications in industry. So it covers things like machine learning, statistics, mathematics, but also industry domains where it's being applied and enables new kinds of applications and use cases. There are some standard machine learning use cases. There's a distinction between supervised and unsupervised learning. What does it mean? Well, in the initial example, I said we have observations from the past. There's a water glass that's falling. And then in the past, we observed whether the glass was breaking or not. Now our target is to predict whether a glass will break or not. And we have these examples from the past where we already know the target value because we observed if the glass is broke or didn't break. If you have a question, please speak up. If not, please mute yourself. Okay, the example was a water glass where we try to predict whether the glass is going to break. It's a supervised learning task. Could you please mute yourself if you're not asking questions? Thank you very much. Obviously we're talking about a supervised task because we have examples from the past and we want to predict a certain outcome, whether the glass breaks or not. And now we have the so-called training data that are the observations from the past that have already the known target variable value, the glass broke or didn't break. And then we have new cases for which we want to predict whether the glass is going to break or not. For example, in real time, we see the glass falling and we immediately can say, yeah, it's probably going to break. And then maybe I try to catch it or to prevent it otherwise, but maybe I have no chance because it's happening so quickly. But there's other use cases, like I mentioned, predictive maintenance, where you try to predict machine failures early enough so that you can actually do something to prevent them. In this case, with the falling glass or with the breaking machine, we have two classes. Either it will break or it will not break. So we have two categories, and the whole classification, or the whole task is called classification. We predict a category, a label. Classify an object or a situation into one of multiple possible outcomes. The glass is going to break, the glass is not going to break, or the machine is going to fail, it's not going to fail within the relevant time period. Sometimes you want to predict a category, then you have classification. Sometimes instead you want to predict a value. For example, you want to predict how many units of your product you're going to sell next month, or you want to predict a probability, how likely it is to for the machine to break. So whenever you predict a numeric value, that's called regression. And an example is demand forecasting, predicting how often a particular product will be sold or how often it will be needed for your production planning, for example. Or in case of the telecom industry and the telecom networks, it could be load forecasting. How many users do we expect in a certain telecommunication cell? Which data volume do we expect the system needs to handle in the next so and so many minutes? So there's a lot of prediction tasks that use regression that could be used to do something like load forecasting, bottleneck prediction, etc. And classification could be used, for example, to predict failure of telecommunication components or certain critical situations. As long as we have data from the past where we could observe and learn how the relationships between the input variables and the output variables were. Like in the example of the glass, the input variables would be thickness of the glass, height of the fall, hardness of the floor, and the output would be the glass is going to break, yes or no. In terms of the telecommunication networks, you will have to discuss what reasonable inputs will be to describe situations and what then the outputs would be. Plus, we also have a context, a time series information, like how, for example, the trend was, whether the demand was growing or not. So there's a lot of things we have to discuss, what kind of data we can consider for using machine learning for classification or regression tasks in Ariadne. Well, this was all supervised learning. We have data from the past, which includes labels, values for the target variable. But there's also so-called unsupervised learning. In that case, we don't have any labels from the past. We may have data points from the past, but there's no classification. What is good and what's not good. There's just measurements. And now the question is, if something new happens, is that something unusual, something that I should pay attention to? Should I give an alert maybe because something very unusual is happening and that might be something critical? That's called anomaly detection. Or sometimes we have just a huge data set, but we wonder whether there are similar situations that should be grouped together and different types of things that should not be grouped together. And finding these groups of data points automatically, that's called segmentation or clustering. And on the following slides, I want to give a little bit more detail on these different types of machine learning before then going into practical applications. But first, let's also look at the process. How do I actually perform a data mining project? Like I said earlier, the standard and most widely used process to perform a data mining project is called CRISP-DM, for cross-industry standard process for data mining. It was defined by companies from various industries. That's why it's called cross-industry. For example, including car makers like Mercedes, Daimler, and also other industries, and also including software vendors for data mining tools. And that was established several decades ago, but it's still the most widely used standard. And there's good reasons for that, because it makes it very explicit which stakeholders you need to involve, which questions you need to ask, which phases in the project you will have. Also that you're very likely to need iterations before you find a good solution. And so the relationship between the individual steps can be iterative. So you typically start with something called business understanding, understand what's actually the goal of the whole project from a business point of view. Then you take a look at the data that's available to solve the problem and to map the business problem to a data mining problem or to a machine learning task. For example, to classification as a problem. Once you have identified the data sources, the next step would be the data preparation. You try to bring the data in a form that the machine learning algorithms can handle it, and you try to take care of data quality problems, like, for example, missing values or wrong data, noisy data as far as possible. Sometimes you want to do additional steps like normalization of data or transformation. For example, in the case of audio data, you would probably be interested in the frequency of the audio signal, and for that it might be helpful to use Fourier transformation. So data preparation means all kinds of data cleaning, data transformation, maybe even data selection or filtering that is needed to come up with a data set that's well suited for the machine learning algorithms. Then you have the modeling steps with the actual machine learning happening, and then you have a validation where you try to evaluate how accurate are the predictions, how well do I meet my success criteria that I defined in the business understanding phase. And if it's good enough, then I can go into deployment. But there's a chance it's not good enough. And then maybe we have to do the process again, go back some steps or start at the very beginning. Maybe we did not consider all the necessary domain knowledge. Maybe there's some things we didn't understand well enough to model, to create the data set good enough, or maybe there was a problem in the data understanding or the data preparation. Maybe we didn't optimize and select the learners good enough. So there may be iterations until you come up with a solution that's good enough. Or in the worst case, you realize with the given data and the given task, you have no chance of finding a solution that's good enough. That could also happen. And obviously, when we talk about use case descriptions, it's very critical to understand the business side. What's the use case? What goal do we have? How do we measure the success? What are the metrics we try to optimize, to understand the data sources, the data types, the data quality. And the more we understand in these two first phases, the better and more sophisticated is our use case description. So of course, the whole cycle will be gone through once we are in the middle of the project, when we're working on the use cases, and maybe even building additional solutions to improve the data preparation or modeling or the whole framework around it. But already in the use case definition phase, it would be very helpful if we at least do a little bit of business understanding and data understanding, answer a few key questions so that we can be sure that we have a common understanding of what the use cases are, and then we have a feeling for what is it that we actually want to optimize, and how do we measure success. Okay, so let's look a little bit closer at the individual phases. So the first step is the business understanding. It's identifying on a high level what are actually the business objectives. For example, what questions do I need to answer to be successful? Or what success criteria do I have? What do I want to optimize? Do I want to minimize cost? Or do I want to maximize quality? Or do I want to maximize reliability? Or do I have multiple criteria that I need to optimize in parallel? Do I have certain constraints? What do I already know about the problem, like challenges, or maybe I already know some of the patterns, some of the relationships, or even some of the causations. Or maybe there are even already existing mathematical models. Maybe they're not refined enough to predict everything, but maybe they already give some clues. So this is about understanding the problem, understanding how to measure and achieve success. And there's a couple of questions we should be asking. Like in the telecom domain, for example, let's say we want to use machine learning to optimize the network traffic or the handling of the network traffic. Then maybe some criteria we have is we want to optimize or maximize the reliability of the network, the ability of the networks to basically perform every task, like perform every communication and every data transfer required. Or maybe it's minimizing cost, like maybe finding what's the minimal amount of equipment we need to have a sufficient level of service. And then the question would be, what is that level of service? How do we determine that? How is it defined? How do we measure the success? Do we measure the cost in euro? How can we estimate the euro amount from the error rates that we obtain? Things like that. Or is there different types of errors? Are they equally bad, or is there certain types of errors that are worse than others? For example, if I do predictive maintenance for telecommunication network components, is it more critical to have a false alert that I think something might break and I replace it before it breaks? But it would never have broken anyway because it was a false alert. Or is it more expensive to risk the part breaking because I didn't predict it, or I failed to act on the prediction? I would guess that probably the failure might be more expensive because I have a network outage and I have to replace it anyway. But yeah, that's something you would have to discuss. Attach euro amounts to different types of errors, or if you cannot attach euro amounts, maybe at least give a ratio between the different types of errors, saying something like error of type 2 is 10 times more expensive than error of type 1, or something like that. And in this sense, we will need to talk about success criteria, let's say network reliability, network throughput, success rate for serving customer requests, failure rates, whatever the criteria are. Then talk about how can we measure them, how do we weight the criteria, and so on. Because if we don't know what we should optimize, there's no way we will come up with the optimal solution. So that's quite critical from a machine learning point of view as well. That we clearly discuss how do we measure success and error types and costs if possible, and then how can we optimize that. And that way we can actually measure the success and the contribution of machine learning, and we can ensure that the optimization goes the right way. The next step is also important, data understanding. To understand what different types of data are available. Like, for example, is it time series data? Is it specification data about the configuration of the components? Is it usage data? Is it failure data? Is it error logs? Is it weather data maybe? Is it textual data of problem descriptions that some operator added? So there may be different types of data, time series, audio, image, text, whatever. Different types of sources, sensors or IT systems or manually collected data. And it's important to think about what are the sources we want to consider, how do we connect to those sources, and in a deeper phase even understand for each data set, what do the actual columns in the data sets mean. We call these columns often also attributes or features because they often describe the properties of a situation or an object. Then we have the data rows. We also call them observations from the past, for example, or from the present, or we call them examples because for machine learning and for training the models, you need examples from the past. So basically the data rows are exchangeably often called observations or examples, and the data columns are often called attributes. And then typically one of those attributes, at least in the case of supervised learning, is the target variable that I want to predict. This is also called a label, and the values for the individual observations then are called labels. They would be the values for the target attribute. So in the business and data understanding, you obviously need some machine learning experts on the table to ask these questions and to then ask more deep questions. But even more importantly, you need the subject matter experts and the business experts to answer these questions. Like they understand where the data is coming from. They know already previously known patterns in the data. They know also how to measure success and what the good solution would look like in terms of certain quality metrics. They can help to verify the quality of the data. And also it could be discussed already what would be a good process given that we find a good solution to the data mining problem. How could we bring it to production use? How would it be integrated with other IT systems or solutions? So what's the overall context? And obviously data understanding can also be used with the tools. You can already inspect the data visually. You can look for statistics like missing values, minimum average values, deviations, and so on. So that could be a tool to help in the discussion between domain experts and data science experts. And these two first phases, business understanding and data understanding, at least on a very high level, what type of data sources are we looking at? What types of data? And on the business side, what do we actually want to optimize? How do we measure success? These kind of questions are very critical from a data mining and machine learning point of view, and we should address those when defining the use cases. Here are some examples of data sources. For example, it could be data from databases or Hadoop clusters, Excel spreadsheets, PDF documents, could be social media, for example, monitoring whether people complain about network outages, could be email data, for example, alert data, could be sensor data from the measurements, could be standard databases or data warehouses where you have records of the historic data. And then on the output side, for communicating results, maybe dashboards would make sense, or maybe some web service that other systems could communicate with, and for example, ask for the prediction, like give me the load of the expected load of the network in the next so many minutes or hours, or give me the probability that a certain component will fail within the next week or something. So there could be web services delivering predictions for certain tasks. Obviously, there could also be other types like web apps or other forms of interaction. For example, when you require user interaction for better insights, so that, for example, users can drill down or filter what they're looking at, or also for giving feedback, for example, if the machine learning generated predictions were not correct. And the further steps we can go over a little bit more quickly because in the current phase of the project, they're not that important yet, but maybe to understand what we will be doing after we have defined the use cases. Of course, we will dive a bit deeper into business understanding and data understanding, but then we will also address the data preparation, decide on which data will we actually use, how to join the data from the different sources, how to align it, to analyze potential data quality issues, how to clean the data, how to transform it is needed, for example, something like a Fourier transformation for audio data, or some transformations to be able to handle textual data, and then maybe come up with a reduced, optimized, transformed data set that we can use to train machine learning models. This can be an iterative process because in general, you would say, well, the more data, the better, but sometimes noise can also be harmful. So sometimes it can make sense to remove certain information if it's more noisy than helpful. It depends also a bit on the machine learning algorithm, how sensitive the algorithm is to noise. In general, the better you do the data preparation, the better will the predictions be that the models can generate, and the more accurate they will be. In that sense, data preparation is a very critical step. Of course, the machine learning itself is also a critical step. It's about finding the patterns in the data, finding a computer representation of these patterns, and a presentation of the patterns that allow explanations and that allow predictions. And there's different types of models. Very simple ones, something like called nearest neighbor, where you look at the most similar data points from the past to make a prediction, basically saying, oops, these were the most similar observations from the past, so I assume the same will happen like in these particular observations, to very sophisticated statistical or bio-inspired models like neural networks or support vector machines or deep learning. In this little webinar, we don't want to dive too deep into the algorithms. For now, we just take it as a given. There are algorithms, you give them data, some label, and they will come up with a prediction. And if it's a categorical thing, we call those classification learners. If there's a numerical prediction that we want, then it's a regression learner. And sometimes certain tasks can be addressed as both, as classification and regression. For example, the machine failure. A classification task could be, will the machine or the component within the next 2 weeks? And then the answer is yes or no. It's two categories. It's a classification. But you could also ask differently. You could say, how long will it probably take until this particular component will fail? And then suddenly it's a regression task. And the answer might be 4 weeks and 5 days. Or you could ask, what is the probability that within the next 2 weeks? So depending on how you ask the question, there's different types of learning algorithms that will help you to find the answer. And sometimes different types of answers for the same basic question could be useful. For example, for the failure case, I would like to have a yes-no answer. I would like to have a confidence, and I also would have the expected lifetime. So I actually would like all three answers. And so that is something we could also discuss in the business understanding phase to understand what information would be useful, what kind of machine learning tasks could be used to address that. So classification and regression, and then there's an overlap where I can actually apply both of them. And then a very critical step is also the evaluation. It's nice if you have a machine-generated model, but how do you know you can trust the model? How do you know it's reliable and robust? And how do you know it's accurately enough predicting whatever you need to predict? So there's different approaches to evaluate that. One is to measure the performance in terms of statistical measures, like how many predictions were correct, how many were incorrect, and then you have something like an error rate or a predictive accuracy. And there's other measures like, for example, if you focus on the critical cases, let's say how many cases of the failures would I have detected, and that would, for example, be called a recall metric. Or whenever the system said it's a failure, how often was it really a failure? That metric is called precision. There's a lot of metrics that give you valuable insights into how trustworthy, how reliable, and how accurate a model is, and how much value it might be able to create in your organization. You can also use these metrics to compare different learning algorithms, different models, and to find the best one for your task. There's a theoretical proof called no free lunch theorem that basically proves that there is no single machine learning algorithm that is best for all applications. In other words, for different applications, different algorithms might be the winners of a comparison. And that means, since we don't know in advance which learner is the best, you will have to compare and evaluate multiple learners, multiple models. And if someone claims they have the algorithm, they have found the algorithm that can solve everything in the best way possible, then that's simply not true. You can really prove this is not possible. For every other algorithm, you'll find problems where the particular other algorithm actually is performing better than the other algorithm for which someone might claim that they are the best. Have that in mind, please, when we discuss certain approaches. So, for example, currently there's a big hype around deep learning, which is a very powerful and sophisticated class of learning algorithms that can solve a lot of problems very well. But beware, they're not the best solutions to every problem. There might be problems where other algorithms are actually better. So even if we will try deep learning for certain tasks, we will definitely also try other algorithms, and there's good reasons for doing so. There's some standard validation techniques. One of them is The simplest one is you have a training set, and then you have a second so-called holdout set. So you show only the training set to the learning algorithm, and then once the model has been trained, you use a test set to evaluate the model to measure the error rate. A bit more sophisticated is the so-called cross-validation approach. In that case, you randomly split your data into multiple parts, for example, into 10 equally sized parts. You give 9 of these data subsets to the algorithm for training, and then once the training is completed, you take the 10th part for testing, and then you iterate so that each of the 10 parts is the test set once, and the other 9 ones are always the training set. This way you can ensure that training set and test set are always disjunct. You don't want to cheat in the sense that you show the test data already in the training phase. It's only shown after the model is finalized, because you want to have a very accurate estimation of future performance, and the best estimate is if you show new previously unseen data. And then the advantage is, since you iterate that 10 times with different pairs of training and test sets, you can actually average the performance that you measure, so you get a more reliable and robust estimate of performance. So that cross-validation is basically the standard for static problems where the environment doesn't change too much. If you have very time-dependent, very dynamic environments, cross-validation may be too simple of a scenario. In that case, there's other approaches. For example, in the stock market domain, when people want to make investment decisions and they use algorithms to predict, for example, stock market prices, there is a validation model called backtesting. You basically take data from the past and then you simulate. Let's say if the algorithm had seen the first section of the data and predicted the second, how well would the performance have been? Then if it had seen the second section and predicted the third, how well would it have been? So you basically simulate how time progresses until only the current data to the algorithm, which then can train or update the model and perform a prediction. Then you continue with the simulation, you validate what the actual error rates were, then you do the next training or update and so on. And this way you get a much more realistic estimate of error rates over time. This is also called sliding window validation, because it's like sliding a time window over your data, using only the data within a certain window for training, and then the next window for testing. And in our domain, in the telecommunication, you will have to discuss, are we looking at tasks that are static enough to use cross-validation, or will we use more sophisticated validation approaches like sliding window validation? And now I talked a lot about validation from a technical, mathematical, statistical point of view, for measuring certain metrics. But there's also other types of aspects in the validation that are very important. Very often you want to have a domain expert to inspect the model to make sure that the relations found are actually real physical patterns and not just random patterns that seem to be present in the sample data that we're looking at, but that are not real physical laws. So in that sense, the human can be like a quality check if every component of the model makes sense from a domain point of view. And for that purpose, it can be very helpful to have human readable models. For example, something like if then else rules. Like if this variable, like if, let's say, if sensor 1 is a value higher than 5, then maybe we should give an alert. And then, or maybe then we expect the machine to fail. And what is sensor 5? Maybe the domain expert knows, oh, this is the audio data, and if the frequency is too high, then this is usually a warning symbol, signal, there might be an imminent danger of breaking the machine. So maybe there would be a recommendation, slow down the processing or replace a certain part. So in that sense, if then else rules or so-called decision trees would be models a human can easily understand and verify. And this human verification of models is also an important step. Sometimes you have more complex models that are too complex for a human to understand. For example, a neural network is like, in a single neuron in a neural network already is a complex mathematical function, but now a neural network is like a combination of these mathematical functions, and that across multiple levels. So you have a very, very complex mathematical functional expression, and almost no human will be able to really understand fully what this formula captures. There's approaches to visualize certain things or to trying to make that more understandable again, but there's differences in how understandable models are, and we typically use a combination of easily understandable human models that we can actually have validated by a human. And also we look at the performance, and at some points we may even tolerate that certain models are not as well understandable if they have a proven validated performance that is better, and we sufficiently trust the algorithms and the underlying data sets. But there is some risk involved there, obviously, if I don't understand the model. Okay, deployment then means we have found a successful model that does accurate, reliable, and robust predictions, and now we want to automate the process. We want to bring the model into production. For example, we could want to set up a process scheduler that repeatedly executes a certain prediction process, or maybe we want to offer a web service that offers the predictions to other IT systems. Or we want to build a web app on top of certain predictions so that a human can inspect the actual time series and the forecast. So obviously there's some aspects that go along with that, like human computer interface aspects, or trustworthiness, understandability aspects, ease of use aspects, integration into other IT systems, also performance monitoring over time. If the models have a decreasing performance, how can I continuously monitor that and update the models? And maybe even other aspects, like, for example, data protection related aspects. Okay, now we have a few example use cases. For example, let's say we have a use case where we are interested in financial outcomes. Maybe we want to maximize profit or minimize cost. And one such use case might be fraud prediction. We want to minimize the fraud. We want to identify fraud to prevent it or to reclaim the lost money. And now the question is, what are the alternatives? How am I approaching this today? Maybe I'm doing random inspections. And how could I approach it using machine learning? For example, having the system provide a score, how likely a certain transaction is a fraud, or how likely a certain person or organization is behaving in a fraudulent way, and then use that score to prioritize whom to check. And maybe with a prioritization by a machine learned model, my fraud detection and prevention becomes more efficient and more effective. And maybe I actually have a lower loss or a higher profit from using or not using the model. And this diagram tries to depict an example where using the model, we have lower losses, less fraud, and we have potentially slightly higher profits. In this case, no higher profits, but definitely lower losses. Without the model and more random checking, we would have higher losses. But there might be false alerts, and that might actually lead to some lost revenues, and there might be a trade-off. Might not be as positive as it is here. Sometimes it's a bit more tricky to decide what the right mix is. So what's machine learning? It's basically teaching computers how to learn patterns from data and how to make predictions. So we have given data from the past. We also call that training examples. And the machine analyzes that data, gets trained on it, and tries to find the patterns. Some patterns might be very obvious. For example, some linear correlations might be easy to see even with the eye. Or if you have a relation between just two variables, it might be easy to see in a chart. But if you have a very complex relation that involves many variables, that means many dimensions, maybe it's very hard to see it as a human. And then the second step is, once you have the model, when new data comes in, you want to use the machine learned model to accurately make predictions. And these predictions are basically based on the model. That means they're based on the data from the past. Like I mentioned before, we have different types of learning. We have supervised learning, where we have known labels, known target attribute values from the past. And if it's a category, then it's classification. If it's a numeric value, like how often did something happen, or how many units of something will I sell, or how much bandwidth will I need in a certain period of time, then it's called regression. So you do have some observations from the past, and from these, and then you also have the so-called labels. Like for each observation from the past, you have a classification to which category it belongs. Here we have a simple example with circles and squares and triangles, and now the data set is basically the set of all objects we observed in the past. And for each object, we have assigned a label, whether it was a circle, whether it was a square or a triangle, and we use that to train a model to automatically detect for a new object whether it is a circle or a square or a triangle. So we can feed in the images, for example, of the objects. And then the training data already has the labels, and for the new data, we will want to derive the label that fits best to the particular image. And some features we could extract, for example, could be the shape or the size, or could be the color, or could be other properties, depending on the particular task we're looking at. Now, when I have new data, a new image without any label, if I feed that into my model, then the model will predict the label. Like it will tell me, hey, this is probably a circle, or this is more likely a square. And some learners do not only provide you a categorization, they also provide you a confidence for each category. So for example, the outcome might be a prediction that says, well, 80% probability, I think this is a circle, 10% it might be a square, and maybe 10% it might be a triangle. And then you would probably say, well, 80% circle, so let's assume it's a circle. But you know that there's a certain risk that the prediction was wrong. And maybe for another object, the classification says, I really don't know what it is. It has a, let's say, 35% chance it's a circle, there's a 35% chance it's a square, and a 30% chance it's a triangle. So I'm so inconfident, maybe I shouldn't make an automated prediction and rather involve a human here. So there's also approaches how you can handle low confidence predictions. Maybe just issue a warning, or maybe get a human involved to get a better label. So classification means we have categorical output variables, categorical target variables with 2 or more classes. In the simplest case, we have something like yes or no, or true and false. That would be a binary classification, but there's also multi-class classifications. Like in the previous example, we saw circle, triangle, square. That was 3 classes. But of course, there can be many more classes. Let's say you want to do automated email sorting, then there would be as many categories as folders that the email should be sorted to. So if you want to sort incoming email to 20 different folders based on the content, then you would have a 20 class problem or 20 category problem. Like I said, in the simplest case, it's binary. You can see you have the green circles and the blue circles. And the classification model in this case could be a line that separates the green and the blue circles. And now there's a little gray circle, and the question is, what category do we think that gray circle belongs to? You have any guesses? Well, I assume most of you would have guessed this gray circle might be blue, because if I assume this is a linear separation between the classes, like depicted by the line in the chart, then the gray dot is on the right side of the line where everything is blue. So I assume this one will be blue as well. So the data from the past helped me to find a line separating those 2 classes. And then this line helped me to classify automatically what color I think the gray dot will be. Now you can imagine if you start moving the gray dot further to the upper left, at some point the confidence of the prediction will be smaller and smaller, and at some point it will flip into green. And that's an indication. The confidence would actually indicate how confident the model is, and that would be something you can use on how deciding whether you want to trust the prediction or not. An example for classification, predicting the email type, for example, is an email a legitimate email, or is it a spam email, some undesired advertisement? And you all know that probably from your email tools, which usually have a built-in spam filter or spam detection, so that most of the email spam you don't even get to see because the system's already filtering it out. And behind the scenes, you could use machine learning to train such a model, and it could even use very simple algorithms. For example, if you use something called naive Bayes, it's a simple statistical learner based on Bayesian statistics that basically counts word frequencies and associates the various frequencies to the different categories, for example, spam and non-spam, that can already predict email spam correctly with about 99.9% accuracy. So for certain easy to solve tasks like spam classification, they can usually be solved with already very simple learners with a very high accuracy. And then a simple learner might have an advantage over a complex learner like a deep learning approach, because the simpler models tend to be more robust. But that depends on the task, obviously, on the type of data you're looking at. Okay, if I have generated such a model, if new emails arrive, I can automatically analyze the content, look for the words and the frequencies in the emails, and then automatically classify into spam or non-spam and sort the email accordingly. So classification was about predicting categories, or in the last example, email folders. Now, in terms of continuous variables or quantities, we use regression for the prediction. Like in this case, for example, if I want to predict the color value, this might be a more continuous task, and then the color value might be something like you picked it here. Maybe it's orange because that's like the most likely value for the target in that certain area. An example might also be weather prediction, like predicting the temperature, predicting the humidity, predicting the amount of rain for a certain time period. Sometimes you might find that certain things are correlated. So humidity and temperature are correlated. For example, temperature does depend on humidity or vice versa. For example, if temperature increases, the humidity decreases because the air can take in more humidity, more moisture. And then I can use some of the variables to predict others. So for example, you could use a regression model to see how certain variables are correlated and also to compute or predict certain numeric values from other variables. So in this particular example, if you used the humidity as a target variable and the temperature as a base variable or input variable, then after the training, you have a model that predicts humidity based on the temperature. And now if you have a new temperature observation, you can actually predict humidity. So classification and regression both were supervised learning tasks. Now unsupervised learning tasks can be anomaly detection. So what's unusual, what might be worthwhile to have a human look at it to create an alert. Also to look at something like associations or correlations, what happens together very often. Like for example, market basket analysis like Amazon does, people who bought product A very often also bought product B. Or clustering, that is, how can we group the data in a way that the data points within a group are very similar and the different groups are much more dissimilar. So the concept is we have some unknown objects or data points, and the goal is to find certain patterns or groups. And since we don't have labels in the training data, this is called unlabeled. So if we don't tell the system that a particular object or image refers to a circle or a square or a triangle, but just provide some features like shapes or colors or sizes, then the system could try to predict or to identify groups and thereby create reasonable potential labels for other tasks. So in this particular example, maybe the system would be based on shape and color, and one group could be the red circles versus the yellow squares, and so on. Looking at the time, I think I'll skip a little bit over clustering, the clustering details. Yeah, it's about finding groups of data points that are close to each other and automatically having, based on distance measures that need to be defined in a domain dependent way, finding groups of similar data points. Yeah, let's skip that one. Customer churn might be something that telecom companies look at, but on the technical networks, that's probably not the most important part. But it could, for example, be an analysis if there are certain types of customers or groups of customers that are more likely to churn than others. So clustering could help to find reasonable groups of customers based on their behaviors, data usage patterns, communication patterns, call durations, etc. So that might be something, and segmentation into different groups of user types. For example, high volume versus low volume users, or very mobile users versus stationary users, and so on. For finding critical situations, anomaly detection is a very helpful tool. You don't have any label of situations in the past that were critical, or you want to find new types of critical situations where you haven't seen any examples in the past. So maybe you have seen certain types of problems in the past. For those, you can use classification and regression to predict them. But for other types of failures, maybe you've never seen them. And that's where anomaly detection kicks in, because it basically it gives you an alert if something is unusual and you should look at it because maybe it's a critical thing. So classification and regression, you had some labels. Here we don't have a label, but there's maybe a data point that's far out. Maybe that's a data point where the data volume is unusually high, or it's a data point where the failure rate of communication is unusually high. There might be certain criteria that we might want to consider in determining what's an anomaly, what's critical, and then this could be automated. Okay. So one example could be detecting fraudulent transaction or insurance claims. In the telecom space, it could also be trying to find intruders or people who try to sabotage the system, for example, by a load overload. So for example, if I send extremely many requests for telecommunication connections in a very short time frame, that could be an attempt to try to disable my communication network. So maybe I want to find that as well. In that case, different information may be used. In case of the fraudulent transactions, maybe I look at the transaction itself, maybe I look at other types of events and data. So in the medical domain, maybe it's hospital data, maybe it's police reports, whatever kind of history may be relevant. And then you try to find anomalies that would basically tell you, hey, this is unusual, please have a look and inspect. Okay, so we have different types of techniques, so we can use different things. For known fraud patterns, we could use supervised learning like classification, trying to identify known patterns where I have examples from the past. And for unknown types of fraud, we would need something unsupervised, for example, anomaly detection. So we have seen classification and regression as supervised learning tasks. We have seen clustering and anomaly detection as unsupervised learning tasks. And that would conclude my introduction to machine learning. Now I have a lot of industry use cases to show. Before we do that, I suggest we have a round of questions because we're already up with 1 hour of time. I will continue after the hour with the use cases for those who can stay online. We can also video record a bit longer, but I would give you a chance for questions now if you have any.
Hello. First of all, thank you very much for this interesting presentation. I have a question concerning machine learning, but it's quite general actually. The first step in order to use machine learning is to formulate the optimization problem. Then you decide whether this belongs to a supervised or an unsupervised learning case. And after that, you are going to select an algorithm. How do you know which one is the optimum algorithm that can solve this problem?
That's a very good question. The correct answer is I don't really know, but I have some educated guesses. Like, for example, I as a person have been doing machine learning for more than 25 years. I've seen a lot of use cases. I have seen a lot of data sets and problems. And the more use cases you work with, the more industry problems you solve, the more experience you have, what kind of algorithm might be suitable for what kind of problem. But it's just a guess. It's coming from your experience, from your gut feeling, so to say. It's not a guarantee. And that's why we never just use one algorithm. We always try to find different types of algorithms, also from different classes of algorithms. For example, we always use something similar as a base reference. For example, linear regression or linear discrimination for classification, or something like naive Bayes. Then we typically also try something very sophisticated, like a support vector machine or some deep neural network. And then we compare. We let basically, that's one of the reasons why we need to define the metrics, how we measure success, because we don't want to trust our expertise. We want to actually really validate what's really best for your data, for your task. And that's why the business understanding is so critical. We need to understand what is it that we really want to optimize. And then we have a chance to measure success of each learning algorithm. And depending on the available resources and time, we can just test maybe 2 or 3 models or maybe 100 different models. So typically, for example, we have something built into RapidMiner called auto model. This will allow you to automatically test 10 different modeling approaches and to also optimize the most critical parameters of the models. But this is maybe just a first start. If you have a real project and a really critical use case, maybe you want to explore more. Maybe you want to explore 20 or 50 algorithms, and maybe you want to do a more sophisticated parameter optimization. And maybe you do not only want to optimize the modeling, but also the pre-processing, and to automatically select the best pre-processing options, like how to transform the data best to achieve better results. So actually, depending on the amount of resources and time available, we will be able to test and evaluate more alternatives. But yeah, the short answer is we don't know which learner is the best. The semi-short answer is experience helps to select good learners. And the full answer is we will have to validate which learner is the best. We don't know it really in advance.
Okay, I understand. Thank you very much.
Yeah, and it can help, for example, to visualize the data, because if you see a very simple pattern as a human already, and you see, hey, a linear line would already help to separate the classes, then you know linear regression will probably be good. Or if you see that rectangular boundaries would help very well, then maybe decision tree would be a great thing. If you see that the class boundary is highly nonlinear, then you will know also linear regression is going to fail, but you don't know automatically which nonlinear learner is the best. Is it a support vector machine, and then which kernel function to use, a radial basis function or sigmoidal function, or is it a neural network, and what type of neural network? And then actually the exploration begins. So first you look at the data and maybe also use your experience from similar use cases and what worked then. So that is a starting point, but to be honest, you always have to explore. In that sense, we don't know what the best learner will be at the end, and we even don't know in the beginning how well we can solve the problem. Maybe the best accuracy we find is so bad that we don't want to trust the model. So that in that sense, we cannot give a hard guarantee. So if you basically tell me, for this model to be useful from a business point of view, we need a minimum accuracy of 95%. Then the problem is, I don't know what the accuracy of the best model is, and I don't know what the best model is. So we would start modeling, validating, and then we would find different models. And maybe the result is the best model we found only had 87%. We didn't reach 95. And then we would say, okay, now we learned it's not solvable good enough in the given time frame, or maybe it's not solvable at all because maybe the pattern in the data is not existing or not strong enough. Or we find a really good model. But even then, we don't know if it's a really best model possible. We just know it's the best model that we found in the search space that we explored. So yeah, the question what model to use is a very good one, and the answer is non-trivial, obviously.
Yeah, thank you very much.
So in the tool we use, like in RapidMiner, we use guided analytics. We have this auto model, so that will automatically test the most widely used, the typically very successful models. But then if you have a more sophisticated project, you would dive deeper and you would try more models. We have more than 100 different learning algorithms available, and we also seamlessly integrate other libraries, like, for example, Python and R, if you want to script a model or use something someone else developed in one of these scripting languages. We also use, for example, Google TensorFlow or Keras, Microsoft Cognitive Toolkit, H2O, Weka, and other libraries, DL4J for deep learning also, because we really don't know what the best algorithm for a particular problem is, but you want to give you the chance to try all of them that you want to try, and then you choose, or we help you in choosing, if you like, what might be the best algorithms. Any further questions? Okay, so I think you have seen a little bit what machine learning is about, what are critical phases in a machine learning project, and our main intention was to give you a feeling for what are the kind of questions we need to answer from a machine learning point of view to define a use case. Like, what kind of data sources do we have? What are the targets we want to optimize? How do we measure success? And these questions we will be asking when we define the use cases. And the slide deck and the main purpose of this webinar was to give you a feeling for what kind of answers do we need, what kind of questions will we be asking. In that sense, the introduction to machine learning is completed for that purpose. However, to give you ideas for what might be use cases that could be interesting in our domain, we would like you to show you some use cases, if you have more time to stay online, from other industries, and also mention some ideas maybe in the telecom industry what we could be doing, for example, bottleneck prediction in a telecom network, or load prediction, or failure prediction, predictive maintenance kind of tasks. But yeah, it depends really on what you consider crucial. You're the domain experts, we're just the machine learning guys having a toolbox and helping you to solve these problems. But you have to define the problem, you have to give us the criteria we need to optimize. And in this sense, we want to show you some examples of business use cases that could be solved with machine learning. So here's a regression task, it's about demand forecasting. In Germany or in other European countries, if you go to a bookstore and they don't have a particular book in store, the book seller can actually order the book. And there's companies called book retailers, and Libri is one of them. It's actually one of the biggest in Europe. And if the bookstore says, I want to have this particular book, and they order it before 5 p.m. in the afternoon, the book retailer, in this case, Libri, guarantees them that they will deliver the book before 9 a.m. the next morning. This is a very strong guarantee that gives some confidence to the bookseller, the bookstore, that they can basically say to their customers, yes, we can give you that book tomorrow if you order before 5 p.m. And for Libri, this book retailer, to be able to give such a guarantee, they have to predict for every book title how often it will be sold in the next week, next month, for every region, so that they have a chance to deliver it in time. So here have very accurate predictions for all kinds of book titles. And this is obviously book titles, but replace book titles by data volumes or call volumes. And then you have load forecasting in a telecom network. So the algorithm would be the same, but the business problem would be a different one that is solved by the same algorithms. So in general speaking, it's a regression problem. I already mentioned predictive maintenance. Here you see a picture of a manufacturing line where industry robots manufacture a car. And now the problem is that the robots might fail. And if a robot fails, then I have to stop the whole production line. I have to repair the robot, which is expensive. And then the loss in produced cars means a loss in revenue. And this is quite a financial pain. And obviously companies want to avoid the costs that come with machine failures and production stops. So predicting failures before they happen and preventing them is a very big thing. And we don't want to do maintenance in fixed intervals, but we want to make it based on the demand. Like maybe a machine was only used very little, so maybe I don't need to replace a certain part yet. Maybe one machine was used very evenly, so the stress on the machine wasn't too big. Maybe another machine was used more intensively and had very high load balancing issues. Sometimes the load was high, sometimes the load was low, and there was a lot of stress on the material. And so maybe that machine needs the maintenance quicker. And now to decide for each machine individually, how quickly the maintenance may be needed. For some, maybe we can save money by doing the maintenance later. For some, we better invest a bit more in maintenance because they're more critically used. And in that sense, we want to do demand-based, machine-individualized maintenance to reduce the number of failures and to reduce the costs for repairs and the costs for production stops. And you can treat this as a classification problem. You can ask, is the machine going to fail within the next 2 weeks, for example, or the next few hours or days? And the answer should be yes or no, maybe with a confidence value. Or you can solve it as a regression problem, predict the time to failure. Like, for example, this part will be good for another 4 weeks. Or no, this part only for 2 days, and so on. And this would allow your maintenance team to set priorities and to avoid failures with a higher probability. Looking at predictive maintenance is interesting because you have very different types of data you typically look at. You have the sensor data, like, for example, temperatures, pressures, vibrations, audio signals, maybe even image data or video data. Then you have log data about what has been manufactured on the machine. Were there any incident reports, maybe even failure reports? You have metadata. What are the kinds of products I'm currently manufacturing? How's the machine configured? You might have additional free text data, for example, the operator of the machine, having a free text logbook, and they say today everything was fine. The other day they say, oh, today we had a problem with strong vibrations, we had to slow the machine down, or we had to replace a part. So the textual information might give additional clues. So for example, we have done predictive maintenance projects with the aviation industry, with the airline manufacturer, with an airplane manufacturer. And if they task an engineer with replacing part A, then they had a checklist and he would just check done, and they would just put that in a folder and never look at this again, because the task was done, everything is fine. But then there was also a free text field where the engineer that replaced part A could say something like, hey, I saw that part B is corroding, it's not a problem yet, but you should keep an eye on that. In the past, they would have just put it in a folder anyway, because the task was replace A, task was performed, everything was good, and they completely ignored the free text. And then they had a project where they started to actually consider also the information in the free text, because obviously the information that part B is corroding is a very important information for predicting when the maintenance for part B is necessary. And you can imagine in the context of planes, it's very critical. If a part fails, then you may have to ground the plane on the airport, which is very expensive because they have to pay the time per minute that the plane is basically standing at the airport. They have to fly in the spare parts maybe, they have to fly in the technician who is capable to replace the part. And then maybe in the worst case, if it takes too long, they have to cancel flights or delay flights. So there's a lot of costs and discomfort for the airline company and for the customers why you want to avoid it. And so having additional clues that might be hidden in free text or audio data or something like that can be very valuable. An example for audio data is maybe sometimes before the machine has a problem, maybe some parts are worn off and they start to rotate less equally, and maybe you have some vibrations going on, or maybe you have a low humming sound, or maybe you have a high-pitched sound. So looking at the audio signal and some unusual frequencies, or which are the strongest frequencies, you can actually sometimes get a clue that something is not going properly. You could use that for anomaly detection in unsupervised cases, but you can also use it if you have observations from the past to find correlations between those audio signals and the failures. And the way it typically happens is the machine learning guy asks the machine operator, hey, when there's this kind of problem with the machine, is there any indication that you could kind of foresee it? And then maybe they say something like, yeah, there is this high-pitched sound and I know something is not going right, and then most of the times within the next few days the machine will break. Having that information, we would then check with the data, do we have audio data? If yes, we will use the audio data. If not, maybe we will recommend to use an audio sensor to get the audio data. And then we would also suggest to do a Fourier transformation on the audio data so we get the frequencies, so we can actually see if we have higher frequencies than usual. That would indicate this kind of problem. So in that case, you see that understanding the business problem or the domain expertise for what is already known about the machine is critical. It's critical to think about the data sources, and it's also critical to think about the data pre-processing, like how do I make the high-pitched sound visible to an algorithm or to a human? Well, I make it visible by looking at the frequency spectrum, and I get that by doing the Fourier transformation. And then it becomes more visible for humans and for algorithms, and the algorithms can actually pick it up. To give you an example, we have done audio-based experiments, and on raw audio data without pre-processing, we had some accuracy like 55% on a two-class problem. So something like failure, non-failure. And random guessing between two equally sized classes would be 50%. So it means 55% is hardly better than random guessing, just a little bit. But after we introduced the Fourier transformation, we were already at 75%. And then we did some additional other iterations with other transformations and feature extraction algorithms, and we could actually bring that accuracy up to 85, 90% just by doing the right data pre-processing. So in that sense, thinking about data sources and how to process them is very critical. Predictive maintenance we have done in all kinds of domains, automotive, aviation, cement industry, wind turbines and components. And I'm confident it can also be done for components of telecommunication equipment. So that might be something to look at if it's relevant for the use case. Another use case from the steel industry is automated quality prediction. Early on in the production process, predict problems before you complete the production, because maybe you can skip some of the production steps and save a lot of money. Let me skip the details on this one. You can have the slides after the presentation if you are interested in details. Another example is finding the optimal mixture of ingredients, like, for example, in the metal industry, if you want to create a certain metal with certain properties, you need additional ingredients, not just the iron, but also other ingredients. And if they're more expensive, you obviously don't want to use too much of them, but maybe you need a certain minimal amount to achieve certain qualities, and that depends also on the correlations between the different materials you put in. So it's a complex optimization problem, and if you solve that better, you can actually lower the cost and increase the reliability of the production process and increase the product quality. Also, again, we don't have to go into too much detail. We've been doing that in the metal industry as well as in the rubber industry for car tires, for example. Other scenarios is you have large volumes of data, for example, in the control center of a power plant or a chemical factory, and you're overwhelmed. There's so much data that you don't even see a problem because you're overwhelmed by the quantity of data. So the question could be, is everything okay? If not, well, maybe you don't even see it. Do you see the little red arrow? Maybe there was something wrong and you just didn't see it because it's hidden in this vast amount of data. So big data can also be overwhelming for humans because the cognitive capabilities of humans are quite limited. So we had a project in the chemical industry together with companies like BASF, INEOS, and PCK to actually detect, predict, and prevent critical situations like undesired emissions or other things. That was interesting because we also looked at different types of data like time series data, alert data, operator nodes, and so on. Again, I will skip the details. Another use case where we have more complex learning tasks, that's not just classification or regression. We talk about manufacturing. We have new product designs, for example, truck engines or dishwashers, washing machines, whatever. And for a new design, we also need to plan the assembly line, and that design has an influence on how much time and cost the assembly will actually create. And in that project, we focused on predicting assembly times and assembly plans for new product designs. And we did that, for example, with Daimler Trucks for truck engines, and we did it with Miele for dishwashers and washing machines or components thereof. It's an example of more complex things. So the input is not just a linear vector of numeric values, but it's actually a 3D design, and the output is not just a category or a numeric value, but it's actually a complete assembly plan. So you can actually solve more complex problems. For the sake of time, I'll skip the other use cases. There's a lot more that we are happy to share. And like I said, we will share the slides. Also, if you want to learn a little bit more about RapidMiner, we will be offering some trainings to you as well, if you like. Plus, there's freely available online material. There's something called the RapidMiner Academy. There's online documentation, online training courses. There's an online community with more than 600,000 registered users in more than 150 countries, where you can also ask questions, and of course, you can ask us within the project. So there's a lot of starting points. So with that, I would like to thank you for your attention. And if you would like to reach out to us, you can just send us an email, for example, to research@rapidminer.com or to infora@rapidminer.com or to me as a person, and we'll try to help. We have a few more minutes for questions. Otherwise, I would suggest we conclude if there's no questions. So, are there any questions? I don't hear any questions. So thank you very much for the attention. Or is there some questions coming? I don't hear questions. Okay, then thank you very much for your attention. We will share the slide deck and we will share the video recording of this so you can share it with colleagues or use it as a reference when thinking about the machine learning aspects or potential use cases. And feel free to reach out. If you have questions, just let us know. We will help to clarify. And we hope for a good cooperation on defining the use cases and finding out where we can best leverage machine learning to help you in your use cases. Thanks a lot.
Thank you very much for very interesting tutorial.
Yeah, very good. Thank you.
Yes, thank you very much.
Very interesting.
Thank you.
Thank you.
Okay, thanks for joining. We will stop the recording now.